So on Monday, we covered double angle identities for sine, cosine, and tangent, where you have sine 2 theta. Oh, crud, here we go. Sine 2 theta, or cosine 2 theta, or tangent 2 theta. Instead of solving for it as though it's an angle itself and then dividing by 2, we actually have formulas that we can use, and it can sometimes be much more efficient. We also saw on Monday that sometimes we have to do it if it says find each using double angle identities. So we need to know the double angle identities. Our other learning target for lesson 5.5, there's a lot more identities in here that if you're an honors pre-calc, you would cover, or that you will cover in calculus. But for what we do in regular pre-calc, we also do half angle identities. So I can use half angle identities to evaluate trigonometric expressions and to solve trigonometric equations. That's our learning target for today. The product to sum identities we don't cover in here. Those are covered in honors pre-calc and in calculus itself. So there are there's 1 for sine, 1 for cosine. There are 3 for tangent, and they all can come in handy. I particularly like one of them, and I'll let you guess as to why in just a minute. That's the one I tend to use the most, but let's look at them. So we have sine of theta over 2. So inside our angle, wow, this is not going to go well. Theta over 2 is equal to plus or minus the square root in the numerator under our radical in the numerator is 1 minus cosine theta and the denominator is 2. And that's all under the radical. So sine of theta over 2 is that. And you can see that in terms of an actual number that makes sense if you looked at sine of pi over 3. Sine of pi over 3 over 2 would be equivalent to that if we did 1 minus cosine of the actual angle and put it in that formula. For cosine, it's very similar in formula, so you just got to know the difference in the sign, because for cosine of theta over 2, I don't know what that is or why it's there. Disappear, go away. Oh well. Hopefully you already wrote down the sign. I'm sorry. Anyhow, actually no, I need to get that off. How do I undo? When did that get put on there? There we go. Cosine theta over 2 is plus or minus the square root of 1 plus cosine theta over 2. And obviously we have to simplify it, so we will have to sometimes rationalize the denominator, though sometimes it'll work out nicely. We won't have to because we'll just get a whole number down there, or a perfect square down there actually. For tangent there are 3. I'll let you guess which one I use the most often, but there are 3, or which one I prefer to use. For tangent of theta over 2, we have the first one, plus or minus, bless you, bless you. This one comes from one of the identities of tangent. Tangent can be calculated by what over what? Sine over cosine, which if I did that, I would actually end up with 1 minus cosine theta over square root of 1 plus cosine theta. So there's one of its identities. Now one of the other identities for tangent is 1 minus cosine theta over sine theta. And one of the other identities for tangent is sine theta over 1 plus cosine theta. Anybody have a guess as to which my favorite one to use is whenever I can?
Third one.
A, B, or C?
C. C.
Raise your hand if you think it's A.
I know it's B.
Raise your hand if you think it's B. Clap your hands twice if you think it's C. I actually don't care for C or A unless it's convenient for the problem. I don't mind C as long as cosine's a value like 1/2 or 1 or 0. What I really don't want down there is square root of 3 over 2. Why? Because in the end I have to do what? Rationalize, and then I'm going to have to multiply by the complex conjugate. Or by the conjugate of it. And I don't want to do, not complex, the conjugate. I don't want to do that. So the reason I like B is even if it is irrational, it's just one fraction in the denominator, I can multiply by the reciprocal and deal with rationalizing the denominator at the end. So my preferred formula for tangent is this one, but that's not to say that the other two don't come in handy depending on what angle you're using or what the problem is. But the one my personal preference is to use that one. So when they asked us to find the exact value of these expressions, on Monday we had angles that were big. They weren't really on our unit circle, and what we did was we cut them in half and said, oh, think of it as 2 times an angle, whatever that big angle was. We cut it in half so we could say 2 times this smaller angle is the angle we're trying to find. We're going to do the reverse here. We're trying to use the half angle formula. I have this small number 75, which is not on my unit circle, but 150 is on my unit circle. So I could do this. I could do 75 times 2 is 150. So then what I'm going to do is say that 75 degrees is really, sine of 75 degrees is really equivalent to sine of 150 degrees divided by 2. Whatever I have in here better match up to the 75 degrees. Sometimes people accidentally divide the 75 by 2. I don't know why, it doesn't really help them. Or when they multiply the 75 by 2, they start thinking they're going to use the double angle formula. It's the reverse. If you take the time to write it out, you'll see, since this and this are equivalent, I'm going to use the half angle formula for sine, which is plus or minus square root of 1 minus cosine over 2. So I have to do plus or minus the square root of 1 minus cosine of, this is our new theta, 150 over 2. And that's all underneath the radical. What happens is that cosine of 150 is actually 1/2. So this becomes 1 minus 1/2, which is 1/2 over 2. What do I do with that? Multiply by 1/2 to clear that denominator of the 2. So it really becomes plus or minus the square root of 1/4. And you're like, oh man, now we got to rationalize denominators. But we don't, because they're both perfect squares. The numerator I can do the square root of 1, which is 1. The denominator I can do the square root of 4, which is 2. So it's plus or minus 1/2 for the solution.
Wait, what did you do for like the 1/2 part, like the first
Sorry, for right here,
Yeah.
I did cosine of 150. Sorry, cosine of 150, which was 1/2. So that's where I got the 1 minus 1/2. That gave me 1/2 over 2, which is all under the radical. But to clear this denominator, I had to multiply by the reciprocal. That's where the 1/4 came from. Yes, sir. So now you're going to look and say, well, I'm at 75 degrees, right? So that's plus or minus 1/2. I'm at sine of 75 degrees. Sine of 75 degrees is quadrant 1. Since I know it's in quadrant 1, I know the answer has to be positive, so it's gonna be positive 1/2. Something doesn't seem right about that. I feel like I totally did something wrong. I used 1/2. Cosine is, I'm like, wait a minute, sine is not 1/2 at 75, sine is 1/2 at 30 degrees, right? So that's wrong. I grabbed the wrong value for cosine of 50. So, minor change, we do need to take this part off. Instead of 1 minus 1/2, cosine of 150 on the unit circle is actually negative square root of 3 over 2. Sorry. I'm going, that answer doesn't make sense. Well, so this is 1 minus negative square root of 3 over 2. Over 2. Should have looked at my notes, then I would have seen it. That's all under the radical. I'm just looking at that part right now. That's all that this was right here. Well, I gotta get rid of that 2, so I'm gonna multiply by 1/2, but not just to the square root of 3 over 2, to the whole thing, right? So that becomes 1/2 plus square root of 3 over 4. Any questions so far? Sorry? Because 1 times negative square root of 3, or 1 times square root of 3 and 2 times 2. Multiply the numerators, multiply the denominators. Now, in order for me to, I have to be able to take the radical of this. Can I take the radical of the square root of 1/2? No.
Of course.
Nope. But I could get that to be one fraction so that I could at least simplify the denominator. How else could I represent 1/2? 2/4. So in that case, I now have plus or minus the square root of 2 plus square root of 3 in my denominator over 4. And I can split up the numerator and denominator so that I can actually simplify the denominator, the square root of 4, which will be 2. So for sine, I'm going to have plus or minus the square root of 2 plus the square root of 3 all over 2. Because I can evaluate the square root of 4 in the denominator. If it was a number I couldn't, let's say it was a 3 in the denominator, then I'd have to rationalize the denominator, and that would get more complicated. But right now it worked out pretty nicely.
Would it still be plus?
And it will be, because we know it's in quadrant 1, it's going to be the positive answer for that. Yes.
Like, so you have the square root of 4 square root?
So I have the square root of 4 in the denominator, right?
Yeah.
And the square root of 4 is 2. So now that denominator is no longer under the radical.
2 plus square root of 3.
Under the radical, yes, we do. It's okay for now. All right, letter B. Tangent of 7 pi over 12. Well, it's not a doubling one, because I can't split 7 in half. I don't have 3.5 pi on the unit circle. But I could double 7. That would give me 14 pi over 12, which is more than one circle, but it might help. So we're gonna try to do that first. Again. Whatever. So if I treat this as equivalent to the tangent of losing half, so 14 pi over 12, or half times 14 pi over 12. Sorry? That'd be 7, oh, this is supposed to be 12. Sorry. That would be, it wouldn't be 7 pi over 6, it would be 7 pi over 12 still. Because it would be 14 over 24. No, I'm not doubling. I'm just saying, right, if I do that, right, then that becomes 14 over 24, which is 7 over 12. So I'm only multiplying the numerator by 2, not both the top and bottom, otherwise I'd made an equivalent fraction. So we're gonna look at 14 pi over 12. Unfortunately, 14 pi over 12 is not on our unit circle either, but I could say, I can simplify it. That's more than, it's more than 1 pi, right? I could, 7 pi over 6, which is on our unit circle. So for tangent, again, I prefer to use this rule right here. So I'm going to do 1 minus cosine, knowing that this angle is our theta, 7 pi over 6, minus cosine of 7 pi over 6 over sine of 7 pi over 6. Cosine of 7 pi over 6 is negative square root of 3 over 2. Sine is negative 1/2.
Where did the 1/2 go?
Which,
Go.
so that's 1/2 times theta, right? Up here, we have, see this right here? Is this a cosine or this is a tangent one? What am I doing? Using the wrong rule. Oh no, I'm using this rule for tangent. I'm just good. See this right here? This is theta over 2. 7 pi over 12, we're writing as 14 pi over 12, which is twice as big, times 1/2, or over 2. So I'm using the half angle formula. So this is 1 minus negative square root of 3 over 2 over negative 1/2. Up top, that's going to become, I'm going to make that 2 over 2 just to try to get to have one denominator, because I've got a fraction on top of a fraction. So that's going to become 2 plus square root of 3 all over 2 because of the double negative. And now I'm going to multiply by negative 2 over 1. And I have to distribute that negative 2 to both terms in the, actually I don't. I could distribute it to both terms in the top, but what's going to happen is I have 1 here and 1 here. I just have to distribute the negative to both terms in the top. It'll be negative 2 minus square root of 3 for that value. Negative 2? Yes. The next one also is obviously not a double angle formula because it's a decimal, and if I cut it in half, it's going to get even uglier.
You can multiply that.
But I can multiply it by 2, which means that it's equivalent to, what is that going to be? 315. It's equivalent to cosine of 315 over 2. So 315 is our theta that we're going to use in the formula. So go ahead and give that problem a try, see what you come up with. Now, which quadrant are we in?
The fourth one.
Yeah, we're in quadrant 4 now. So if this is cosine, is it going to be positive or negative in quadrant 4? All students take calc or a smart trick class. It's going to be positive. So we know right now our answer is going to be positive for this value. Oh, wait. Well, that's for 315. That's not really what we're evaluating. Which one are we evaluating? We're evaluating 157. So this is the 315 is going to help us get that answer, but the 157.5 is the one we're actually evaluating. And that's in quadrant 2. So we're actually going to take the negative of that answer. Now, up top I have 2 plus square root of 2. over 2, when I change this to 2 over 2. And I'm going to multiply by negative 1/2. And that gives me 2 plus square root of 2. Actually, if I distribute the negative, it's negative 2 minus square root of 2. Because sine, or not sine, oh no, it's not a negative, it's just a 2. Sorry, it is just a 2. I don't know why I did negative. So it's just going to be 2 plus square root of 2 over 4. And we're going to do the radical of both of those. So basically, I end up with negative square root of 2 plus square root of 2 over 2 as the final answer.
Where'd you get that half?
Yeah, I don't.
Where did I get which half?
Like, where you multiply?
See, I had a denominator of 2,
Yeah.
and I had a fraction over a fraction. So that's why I multiplied by 1 to clear that denominator. And it also gave me a new denominator of 4 that was a perfect square.
When you have 2 plus root 2 over 4, like towards the end.
Yes.
You square both.
So the square root was over the whole thing, right?
Yeah.
So what I did was set, one of our rules is the square root of a over b can be represented as square root of a over square root of b. So I just said, let's do the square root of the numerator and the square root of the denominator, because I actually can, one of the rules, you're not allowed to have a radical in the denominator, you're not allowed to have a denominator under the radical. So by separating these, I can evaluate the square root of 4, and now it's simplified. All right. Our last concept, solving the equation over the interval of 0 to 2 pi. So even if it's a tangent function, I don't just look at 0 to pi, I have to look all the way around the unit circle, unless I was doing it for all values, and I can do 0 to pi and add the plus pi in. So we're solving using half angle, okay? So again, some people might say, oh, I'll just solve and then I'll multiply my angles by 2. That's what we had done before. But if on the quiz or the BA it says, solve using half angle identity, and even if it didn't, sometimes it's easier, but if it says that, that's the way you need to do it. So, solve each equation on that interval. We'll figure that part out in a second. First off, we have to figure out how we're going to solve it. So, we have a problem. I have sine and sine squared. That's not a problem. I could factor. No big deal. But I also have a cosine. And it's not connected to a sine, so I can't just factor sine out. Well, it might not work out so nicely. If I were just trying to solve right now, I'd have to square. I'd probably move this over, try to square both sides. It's going to get ugly real fast. So this is why you're going to want these angle identities, because if you see this angle right here, you're like, oh, well that might help simplify it a little bit. I know the half angle identity for sine. And I just have to remember that it's supposed to be squared and doubled after that. So right now I have 2 times something squared. Well, that sine of x over 2 is what's in there, sine of x over 2. Using our identity of the plus or minus the square root of 1 minus cosine, 1 minus cosine of x over 2 is going to come out to be really handy in this case. Why? What happens? Cosine doesn't necessarily cancel out, but the squared and the square root and the radical, they go away. They're inverse operations. So now I have 2 times 1 minus cosine of x all over 2. Well, the 2's cancel out. So now I have 1 minus cosine x and the rest of my equation plus cosine x. So yes, some of you said that cosines cancel. They did. You got a couple steps ahead of us. Equals 1 plus sine of x. So the cosines are gone. When I subtract 1 to get sine by itself, I get 0 equals sine of x. Well, where's sine 0? In 2 places. 0 and pi.
How'd you get 0? Because 1 minus 1.
I got 0 because I had 1 plus sine over here, and so I was taking away 1 to get sine by itself. And so that gave me 0 here. Letter B also has a half angle identity. When you see those expressions like 2x or x over 2 in the equation, you want to see if that can help you. Okay? By the way, there's a particular one you're probably going to want to use, and it's going to involve what term in it? What term do you want it to involve? Cosine, because you see there's a cosine in the equation already. So, you can pick any of them, but I would probably not do the one with the big square root. I'd probably go with option B above, because that's just my preference. So go ahead and give that a try. See if you can remember that you have 8 times whatever ends up being in there, plus 8 cosine times whatever ends up being there equals 1. Bless you.
The angle we don't know. We're solving for.
So, yeah, we're going to figure out what the angle is eventually. So what did you do, the 1 minus cosine over sine?
Yeah.
That's the one I would go with. The other ones will work out too, but this one always looks, I like this one better. Well, both of these now have a denominator of sine. I can't divide by a trig function to cancel it out, but I can get rid of denominators by multiplying by the common denominator.
Yeah, why isn't it the cosine?
Why is it what? No, this is tangent.
But it's,
This is tangent. So I'm rewriting tangent of theta over 2, tangent of x over 2, the half angle identity for tangent. Letter B up here that we looked at, oh, what a mess, is 1 for tangent. This isn't for cosine, this is for tangent. 1 minus cosine over sine. You could go with one of these other options if you want, but your denominator is a little more complicated with that. So I decided to go with this identity, as letter B as identity. So now, I can distribute my 8. I have 8 minus 8 cosine of x plus 8 cosine x minus 8 cosine x squared equals 1. And this all has a denominator of sine, right? Sine of x. I forgot to put the x on it. I don't want to deal with this as, I can't eliminate sine, but I can move it to the other side.
the one
Would it
cosine.
be 1 over sine?
I can do 1 over sine times it. Oh, but it's equal to 1, so that's not going to help me. If it were equal to 0, that might help me.
Can't you cancel the minus 8 cosine of x? Plus 8
That I
cosine?
can do. That I can at least do, yes. This term and this term are opposite, so they can go away.
Why is that one squared? That gives never mind.
Because I had 8 cosine times negative cosine. So now I have 8 minus 8 cosine squared x equals, I don't like having a denominator, so I'm going to multiply by sine to clear that denominator. You can leave it there if you want for now. It may actually help you out. We'll see in a second. What am I going to do now? I could factor out the 8. I don't know that it'll help me. I was going to do it separately, but that works. I was actually going to just convert this, but that's a good idea, Sarah. Just factor out the 8, and you're left with 1 minus cosine squared x, which is a Pythagorean identity. I was just going to use the Pythagorean identity here and then distribute the negative 8. Both will work. So this becomes 8 times sine squared equals sine of x. Can I divide by sine?
Yeah.
Absolutely not. That's like dividing by x. But I can move it to the other side, not through division, but by subtraction.
Then we just
and now we'll factor out sine of x by 8 sine of x minus 1. Said both factors equal to 0, we have sine of x equals 0. Well, that's easy. When is sine 0? Sine is 0 at 0 and pi.
What about the 1?
What
Remember,
1?
didn't it equal 1?
It did. It did equal 1, but then remember I multiplied it by sine, and 1 times sine is sine
Oh,
is sine x. So I don't have to worry about the 1 anymore. Now, if you still have it as a rational expression with sine in the denominator, then yeah, you're going to have to worry about the 1. And then my other factor, the 8 sine x minus 1 equals 0. I'm going to add 1 and divide by 8. Sine of x equals 1/8. All right, so we have two answers here. Without a graphing calculator, because there will be a part of the BA that would not have a graphing calculator, you won't be able to do this part because it's not on your unit circle. But with a graphing calculator, you could do this. Or if I said, give me other functions, you could draw your triangle and tell me what cosine and tangent would be. But I'm actually asking for the value of x, so I'm going to do sine inverse of 1/8. And I want to make sure that I have my calculator in radian mode. Most of us do. That's 0.1253. Is that my only answer though? Where, this is in which quadrant if it's that small of a value? It's in quadrant 1, which is what we get when we do sine inverse quadrant 1 or quadrant 4. So my answer is over here in quadrant 1. Where else is sine going to be positive? Quadrant 2. So how am I going to find the other value? 180 minus, well not 180, would be 180. Pi minus 0.1253, which is 3.0163. As long as I've just kept it in my calculator as well. So there's my 4 answers, 4 possible answers for this. Now I don't have to worry about as much about checking for extremes because I didn't square anything along the way. It was already squared in the original equation. So your assignment is on the assignment sheet as page 352. (28 to 36) and 91 to 97. And if you were not here the other day for 5.5 day 1, that assignment's also on the backboard and on the 5.5 part 1 notes.